Welcome to this course on variable selection. In this course we're going to discuss many aspects of variable selection. Firstly, why we want to select variables, and then what methods are available, and importantly, how to choose between these methods. We will do a lot of practical exercises in order to get experience with how to perform variable selection in practice. During the course we're going to use a dataset of 61 beers. These beers have been measured by visual and near-infrared spectroscopy, and the spectra are shown in the plot here. If you look at the visual area, around 400 to 600 nanometers in the plot, you will see that there's a lot of variation, and that's because the beers range from very light to very dark beer, and so the color is different among them. What you will also notice is that if you have some experience with spectroscopy, then the high wavelength area is very noisy, and in fact an absorbance of about 3 to 4 is quite extreme. This dataset is nice for illustrating variable selection because it has different properties that are also useful in other contexts. For example, the high variation that you see in the visual area is not at all informative with respect to what we want to predict, but as I said, it has a high variance, and that can influence the model. Also, the noisy area to the right is not very useful. So we have examples in the data of variables that are simply noisy and other variables that are systematic but not at all important. And in this example it's very easy to see visually why and how this is. That's not always the case in other types of data. What we're going to do in this case is trying to build a calibration model, trying to use the spectra to predict what is called real extract. Real extract is a quality parameter in the beer production, and we're going to see if we can build a fast method for predicting that from the spectra. So on this page you can read a little bit about the data, so you can do that before you actually try to build your PLS model. Now that you have tried to build a PLS model, let's talk a little bit about why we want to do variable selection. In many cases, people consider variable selection simply because they want to improve predictions. And that is a perfectly valid reason for doing variable selection, but there's actually a lot of other reasons for why people want to do variable selection. Sometimes it's just to improve the model. For example, you want to get rid of noisy variables, or you want to improve statistical properties, or as I said, you want to improve the predictions. But it could also be for interpretation. Maybe you find it easier to interpret a model if you remove variables that do not really contribute constructively to the prediction. So maybe in fact you don't want to improve your predictions, but you may want to simply maintain them, or even have slightly worse predictions but have a much simpler model that is easier to interpret. Another example of how to use variable selection is that you may want to build a calibration model based on high resolution spectral data, for example. But in the end your model is going to be applied on a simpler instrument, maybe a filter-based instrument, so you want to find out which part of the high resolution spectrum are you going to use in the final filter-based model. And that's useful for building, for example, online instruments with simpler instruments than the lab instruments. So how can we do variable selection for all these various reasons? Well, as you can see in the list here, there are many different approaches to variable selection, and we will touch upon most of these in the following. The list is not exhaustive, but you can see that there are some generic terms. For example, a-priori based variable selection, meaning how to choose your measurements. In the following we will go through most of these generic types of variable selection, and we will discuss when they are useful and what you should know about your data before using the various types of variable selection methods. Before we discuss what methods we have available for variable selection, it's important to discuss how to evaluate how well our variable selection is working. And this is important because there are some pitfalls. A very naive approach would be to say, why not just choose the best variables? Even though it sounds simple, it's not so simple to define what actually best is, and also it may not be physically possible to evaluate all the different possible combinations of variables. Let's say that it takes 0.1 second to calculate a specific model, and let's say that we have 4 variables. Well, then we could test all combinations of these 4 variables, and it would only take us a few seconds. If we had 10 variables, it would take us 100 seconds, and if we had 20 variables, it would take us more than a day. With 30 variables, it would take us approximately 3 years to calculate all combinations of models. So even if we could define what best is, it would be physically impossible to try all the combinations. And also we would risk overfitting tremendously because of all the combinations that we looked at. Even if we could test all the combinations, we still have to define what good is. Let's look at an example where we have, for example, 10 samples and 1,000 variables. And in this case, the data, all the 1,000 variables, are relevant for predicting our dependent variable. So we could select, for example, just one variable that correlates the best with the dependent variable. If we take a new set of similar samples, for example 100, we will see that this variable that was chosen actually leads to a good model that can also predict new samples. But let's look at the same example in a situation where the data is not relevant. So we have 1,000 variables, but they are not really correlated to y. Randomly, some of these variables will correlate to a certain extent with y, and if we pick the best one, we could get a fair correlation as shown in the plot to the right. But if we test this model on new data, we will see that it is absolutely not predictive at all. So this definition of best based on the 10 samples that we had was actually not a good definition, because it turns out not to be able to predict in the future. Let's look at the first type of variable selection method that we have. That's a simple one. It is choosing the right measurements, but that's actually the most important way to select variables. It's really beyond the scope of this course, so we're not going to discuss this in detail. But naturally it is important to choose measurements that are relevant for your problem. There's an important aspect of this that is not always considered, and that is that you may have indirect correlations in your data which are difficult to predict beforehand. So don't let your a priori knowledge guide you too much in selecting variables. It's better to include more variables than to exclude variables. Then you can test in practice whether these variables are actually useful. Here's an example dealing with dioxin contamination in fish oil. This is a big problem in the fish industry because of regulations and because of increasing levels of dioxin. So the fish industry is interested in measuring dioxin levels. That's very expensive and very slow today, so if a fast method could be developed, that would be interesting. Here's an example where fluorescence spectroscopy was used to measure different oil samples, and in fact it was possible to predict dioxin from the fluorescence. Here you see the predictions, the predicted PLS predicted dioxin level from the fluorescence spectra versus the reference dioxin level. In this case there is no information in the fluorescence spectra about dioxin. because of the low dioxin concentrations, there's no way that fluorescence can actually measure that. Still, we can predict, and in this case actually sufficiently well, predict the dioxin level. So this is clearly an indirect relation, probably a biologically induced relation. But if it's valid, it's still useful, and if we want to predict the dioxin level, well, then we can use a method like this. And there was no way that we could have known beforehand that fluorescence would actually be able to do so. So this is an example showing you that sometimes it can pay to be a little bit exploratory in selecting variables. There are also other reasons for why you don't want to remove too much potentially irrelevant information beforehand. Here's an example in the plot below of a chemical system consisting of two chemical analytes. And what we see in the upper plot is the pure spectrum of the analyte, that's the blue one, and the pure spectrum of the interferent. This is of course simulated data, just to illustrate a point here. Now, if you look at the blue and the green spectrum, you can see that there's absolutely no overlap. Mathematically, it will then hold that if we build an empirical regression model, such as a PLS model, based on a number of samples with these two analytes, well, then the shape of the regression vector will be exactly identical to the pure spectrum analyte. So the regression vector is a measure of the amount of analyte. Now in this case we could actually have cut off the part of the spectrum to the right of the upper plot, because there's no information about the analyte and there's no overlap. But let's look at another situation. Here we have a different set of spectra. In this case the interferent, the green one, is overlapping the blue one. And now the regression vector is not identical to the pure analyte spectrum. In fact, it's identical to the analyte spectrum orthogonalized with respect to the interferent. So it's the blue line in the upper right plot orthogonalized with the green line. What's interesting here is that you note that the width of the spectrum that we're using in the regression model is now broader than just the analyte spectrum, because we have to correct for the green interferent, and the green interferent appears outside of the area where the analyte spectrum is. And such a thing is difficult to predict beforehand. So some people would argue a priori that they should choose, for example, the part of the spectrum where the analyte appears. But that will not always lead to optimal predictions, because sometimes the model would want to correct for interference, and in order to do so need to have as good information about the interferent as possible, and that could possibly mean including areas that are absolutely unrelated to the analyte but related to what the model has to correct for. So let's have a look again at the beer data. You try to build a PLS model trying to predict the real extract, and let's have a look at how a model of real extract will typically look. Here's an example of predictions using the whole spectral range, and these are the cross-validated predictions. We have a correlation of 0.96, and we have an error, an estimated average error of about 0.7, which is fairly good given the range of extract from 5 to 18, so we have a fairly low prediction error. But let's see what happens if we do a little variable selection. Well, based on chemical insight, we can hypothesize that the visual area is probably not very relevant, even though there's a lot of variation. So the low area in the plot here, the left area. Also, the area to the right is very noisy, and it's probably not containing much information at all. And in fact, in the middle area here, we have and a part of the near-infrared spectrum which should be indicative of real extract. So if we only use this middle area here and build a PLS model on that, well, then you see that we get much better predictions. Even though we had a good model beforehand, the error, the average error, is now only a quarter of what it was before. So this is actually a huge improvement based on selecting a small subset of the original variables. Now, this whole course is about how to achieve results like this. In this specific situation, we had a lot of background knowledge, and that could help us and guide us to getting a good model. But in many situations, we don't have that background knowledge, and we don't have a data type of data that looks like this, where we can actually from the raw data see a lot of properties directly. Sometimes you may have discrete variables and you cannot see that a certain area is noisy, you cannot see that a certain area has a lot of variation, etc. That's much more difficult in other types of data. So we will use this data set throughout and see how more automated methods can come to similar conclusions as the ones we have reached in this example. The first approach that we're going to look at for variable selection is what we can call model-based selection. And it's simply based on looking into how a model achieves its results. So looking at loadings, regression coefficients, etc. There is an important assumption if you want to use model-based selection. And essentially the assumption is that your model has to be valid. And in terms of a calibration model, that means that your model must be able to predict. So you must be in a situation where your cross-validation or test set validation is working, so it's showing you that you can predict. If that's not the case, well, then the model is not reflecting something that's predictive, and therefore you cannot use the model to explore details of how important different variables are. Because if the model doesn't predict, well, then it's essentially nonsense, and you may remove important variables or at least get the wrong conclusions when you try to interpret the model. In some situations, especially if you have very many variables, for example in MS spectroscopy or NMR spectroscopy or in gene array type of data, well, then it's very common that if you build a model on the whole data set, you cannot actually find a valid model, and then there's no way to look into it. So you have to be in a situation where your validation works. Let's look at a small example. This is an example from sensory analysis. In sensory analysis, humans are used as instruments to judge, for example, food products. In this case, 8 different persons assessed 10 different breads with respect to 11 different well-defined attributes, different sensory descriptors. So we get a three-way array of 10 by 8 by 11, and we average over the 8 judges as we see them as replicates, so we get a 10 by 11 matrix. And from that matrix we want to predict, in this case, the salt content. Before we start looking at the model, we have to check that the model is valid. In the lower right, we see the calibrated and validated variants for this specific PLS model. The purple bars are showing the cross-validated error, and we can see that we have 3 or maybe 2 components, and indeed the gap between the validated and calibrated variants is small and high, so that indicates that the model is valid. So then we can take a look at the upper left loading plot, where we see that there are 3 variables that seem to have very low coefficients, very low loading values. And we have to stress that this is only the first 2 components we're looking at here. In this case, you might argue that we have a 3-component model, and therefore it's not enough to only look at the first 2 components. But in this case, we'll stick to the two components just to keep it simple. But in reality, we should look at all the relevant components. So, 3 of the variables seems to have very low influence on the model, and therefore possibly could be eliminated. We can go a little bit further into detail with this. In the lower right we see the variance explained. That's the total variance of the model, of the predictions. But we also have a model of X that we can take a look. To the right we see the explained variance of each of the 11 X variables. And what you can see is that there's a huge difference between the calibrated and the validated variance for 2 of the components, the bread odor and the variable called sum. So that is, if you look at the calibrated variance, the model thinks that it's doing quite well, explaining 50% of those, but in reality when you try that on a new set of data, or as here during cross-validation, what the model is modeling is actually not consistent with what is seen in new data. So clearly these 2 variables are absolutely wrong, and it's likely that we will improve the model by removing these 2, and that's also the reason why they had a low loading. On top of that we have the color, which also had a low loading, but it's not inconsistent, it's just not very valuable. So we can also remove that one, and possibly it will not improve our predictions very much, but it will lead to a simpler model if that's what we want. So now we have removed all 3 of them, and in fact we did get a better prediction. If you look at the loading plot now, you can see that some of the variables are very correlated. For example, the variable called other taste and off flavor, because they are close to each other, far outside in the model, so it seems that they are giving more or less the same information. Again, we have to remember that we're only looking at 2 of the plots here, and if we think that we have 3 components, we also should take a look in the 3rd component before we draw any conclusions. But as just from this, we can remove some of the variables because they seem to be correlated to some of the other variables, and possibly we will not improve the predictions, but we will get a simpler model if that's what we want. There's another set of tools that you can use for selecting variables. In particular, there's something called the variable importance for projection, or VIP. It's a measure, a combined measure of how much a variable contributes to describing Y and describing X. So it gives you an indication of whether this variable is well founded in X as well as important for predicting Y. Let us take a look at the VIP scores for the beer data. Here we have a 4-component model of the beer data, and first let's take a look at the loadings. When you look at the loadings, it's easy to see that the visual area seems to be important, and it's also easy to see that there's a lot of noise in the high wavelength area. Now the reason that the visual part of the loadings has so high values is due to the high variance in that area. We do know now that this part of the spectrum is actually not important for predicting real extract. The regression coefficient is actually what represents the prediction. This represents what part of the data is used for predicting Y, in this case the real extract. The regression vector is just a linear combination of the 4 loadings above, but it's amazing to see how the visual area is completely cancelled out, which is a good thing. So the model has been able to separate out the important part of the variation with respect to the visual area. It's easy to judge the regression coefficients here and see what parts of the data are important and what parts are not. Essentially the left part is almost 0, which means that we can eliminate that. Also, the right part is very noisy, and we can see that because we have a smooth spectra, and therefore we could also eliminate that. If these data had not been smooth and continuous, it would have been more difficult to assess this noisy area, because we can see that due to the noise, some of these variables do get high values. But in this case, we know that this cannot represent real information, because if one variable has a high regression coefficient, then its neighbor per definition should also have a high one, and that's not the case. If we now take a look at the VIP score, we can see that the VIP score is different from the regression coefficient. The regression coefficient tells us exactly what information is being used for predicting y, whereas the VIP is also telling us something, which part of x are important for that prediction. And we can see that in this case the visual area is important, because it's important in all the four components used, and therefore it's being judged as important for spanning the variation. In the VIP score, you can judge the relevance of a variable from the red line, which appears at the value 1. So variables far below 1 are seemingly irrelevant, whereas variables that are far above 1 are highly relevant. Normally, one would not eliminate all variables below 1, but would perhaps take some of the more obvious ones, the ones with the lowest values, and also in this case take a look at the spectral smoothness. So for example, in the noisy area, even though some of the variables do have values higher than 1, they would probably also be eliminated. As just from this example, it seems that the regression coefficient is a more relevant measure of relevance than the VIP, but that's not always the case. In some situations, the regression coefficients are very difficult to assess due to noise, because for statistical and mathematical reasons, regression coefficients tend to be quite noisy, sometimes very noisy, and that means that it's difficult to assess what variables are important. The VIP is often more clear there. Also, the VIP is misleading with respect to the visual area here, but this is a very special situation, and even in this case, using the VIP, it is possible to derive a good model. And this is exactly what you are going to try now. So you should use VIP and also possibly some of the other measures to see if you can improve the PLS model that we made before. Summing up what we have talked about now are some of the more trivial types of variable selection. First of all, to measure the right thing. Also, to take into account that even though we know exactly what parts of the data would be directly related to our variable of interest, then there could be indirect correlations that would lead to better models if those variables were included. And here in the last part we talked about using the calibration model for improving it, looking at loadings, looking at regression coefficients, looking at VIP scores, etc. But this is only possible if the calibration model is working beforehand. If you are not able to find a model that works, well then you're not able to assess the loadings, the regression coefficients, etc. at all.